I want to talk about what we're going to do today in preparation for Lab 2 next week. And as promised, kind of 2 boring theory lectures this week, and today is a lot more practical, so hopefully more fun. That is a lot more fun for me to teach as well. So here's the motivation for Lab 2. Lab 2 is a relatively new lab in the last couple years with a focus on debugging. Meaning, rather than coming into lab and building a circuit, you are going to come into lab and the TAs are going to hand you a pre-built circuit that is intentionally broken. So there are 1 or more things wrong with it, and it is your job to figure out what is wrong and fix it. And this is very much in preparation for the robot project later this semester, because I do not want you to come to me on Monday saying we spent all weekend pulling our hair out because we couldn't get our robot to work, and then we realized there was literally 1 wire in the wrong place, okay, that was just preventing the whole thing from working. And in terms of learning outcomes of this class, I do not care if you remember how to do node analysis in 5 years, right? Or you have the capacitor equation memorized, okay? That is information you can go look up. Google, Wikipedia, YouTube, ChatGPT, a good old-fashioned textbook, whatever, okay? You can go look up an equation. But you cannot ask ChatGPT, at least not yet, to fix your robot for you, right? Maybe give it a couple decades, but you can't hand it your robot and say, hey, my robot's not working, why, right? Learning to debug a complex system and isolate and identify the problem is probably the most important practical learning objective from this class, okay? I gotta teach you the equations, they're boring, you can go look them up later. But the debugging is something that I think is a lot harder to teach. It is a practical skill that takes practice and experience to learn. So that is very much the motivation of what we're doing today in Lab 2. And again, we're going to see how long it takes me to catch my breath, and if I can just get through a 50-minute lecture without sweating more and running out of breath and talking too much. We'll see. Okay, so that is I'll get off my soapbox thing for a minute. Today we are going to be talking about buttons and switches. And we'll switch over to Tinkercad in a minute and look at how to use these. With the context and the backdrop, and being specifically thinking about debugging, we're kind of going to look at a couple different things. One is how these are wired, right? So I think I mentioned back on day 1, you might buy, there are lots of electronic parts that are literally a little black box, right? Like we use the phrase black box figuratively sometimes to mean like something where the internal workings are not visible or obvious to you. This is literally a black box, right? It's a little black plastic case with some connections inside that I can't see. So it's not immediately obvious how are these pins electrically connected and what happens when I push the button or click the lever or whatever. We're also going to talk about this in the context of failure and things breaking, right? Like we talked about fatigue failure. For those of you who took 30-70 last time, you have a giant, I'm not going to pull all these out, right? But you all have a bag of parts, right? And I can tell you from a decade, more than a decade of experience, both with teaching this class and doing robotic stuff at the K through 12 level, that people build a circuit and it doesn't work, and your first instinct in the lab is to raise your hand and tell the TA, it's broken. Okay, I follow the directions, I know I did not make a mistake, there must be something wrong with the equipment. And I can tell you from experience that 95 times out of 100 it is user error. Okay, and that is not just at the college level, that is at the K through 12 level, where I will get an angry email from a parent that says, hey, I bought your kit and my kid's science project is due tomorrow and it's not working and the directions are wrong and you're dumb and I hate you, give me my money back, right? Like, and then they say, could you please send us a picture of your breadboard? And they send a picture and I go, could you please move this wire from row 2 to row 3? And then it all works, right? So like I think it's just human nature that you don't want to assume you're the one who made a mistake, but 9 times out of 10, that's what happens. So, but that does not mean that parts never fail, right? Like I said, 9 times out of 10, not 10 times out of 10. It is very unlikely for these parts to be broken, when they are brand new out of the box, but the components in your kit have been reused for years, right? So your predecessors, alumni, students before you, the seniors, have abused these in the lab, right? Particularly the battery packs are a big point of potential failure that we're going to talk about a little more today, time permitting. But first, I want to talk more about buttons and switches. So we're going to go to the next poll everywhere, and I believe this one should actually have, oh no, that does not have an embedded image, so hold on. I need to open Tinkercad and switch over to the projector, because I forgot that I didn't embed the image in the poll everywhere. So, give me 1 second. Find the HDMI cable. Those are all USB. That's really good. It's over here. Okay. I'm going to activate the poll, but you can't actually answer it yet because you can't see the Tinkercad. Okay. So, the poll everywhere, I'm going to zoom in so you can see this a lot better. I have a breadboard with a battery connected and 4 LEDs with a corresponding button. The question is, which LED will light up when I press the corresponding button and remain off when the button is not pressed? Okay, the poll should be activated. I'm not running the simulation yet, you're just looking at how this is wired. Okay, which LED will be off when the button is not pressed, will turn on and stay on when the button is pressed. And again, this is just participation. There isn't I don't think I put an I don't know answer in here, so if you have no idea and don't know how the buttons are wired, just give it your guess best. There is no I don't know option. Okay, we're around 100 replies, so I'm going to give it another 15 seconds to wrap up. I hear some good discussion, but I want to make sure we have time to get through the other stuff I have set up for today. So 5, 4, 3, 2, 1, deactivate. Okay, the correct answer is D, but only about 1/3 of you got that. So yeah, a lot of people said A, and so this is tricky. If you've never worked with these before, it's not immediately, like I said, this is a thing with 4 pins. Just looking at the exterior, it's not clear, let's turn my mic back on, yes, how those pins are connected, excuse me, that's what data sheets are for. So, we're going to switch over to the document cam and look at a data sheet for this thing. Now, data sheets, different parts from different manufacturers, are going to vary in quality, right? Some of them will have a ton of information on them, right? Like this one has very detailed dimensional drawings. It's also, this is way too small to read, but over here on the right, there's a bunch of different variations of this part with, I think, different colors for the buttons and things. If we zoom in, some of this is so small that I can barely read it here. You'll get things, even like the actuation force, how hard you actually have to push on the button, how far it moves, so the actuation travel, life expectancy, electrical stuff, so the rating for what will actually burn it out. The contact resistance, so remember we talked about different scales of resistance. So in the circuit diagram in physics, we treat the switch as ideal. In reality, the contact resistance is about 100 milliohms. So if you put one of these in a circuit, it's like adding a 100 milliohm resistor in series with something. All sorts of details, right? What we care about right now is figuring out, oh, there's this tiny little diagram here that shows us how the damn thing is actually wired, right? So what this diagram is showing us is that there are 4 pins, but the 2 pairs of pins are always connected across the button, okay? So pin 1 is just hardwired to pin 2, pin 3 is hardwired to pin 4, and when I press the button, then it's connecting all 4 of them by closing this switch in the middle, okay? Tricky part, annoying thing about these data sheets, is the orientation of the pins in this diagram does not always match the orientation of the pins in the physical part. So look, this starting in the top left goes 1, 3, 4, 2 clockwise. If we zoom out and go over to the physical diagram, look, this is like mirrored and rotated. Let's see. That goes 3, 1, 2, 4. So it's mirrored, right? So this one has 3 and 4 on the left. That one has 3 and 4 on the right down there. So that is a, we've talked a couple times now about how geometric layout in the circuit diagram with resistors, say, being geometrically parallel to each other isn't the same as electrically parallel. Be careful with these data sheets because sometimes the circuit diagram and the physical layout can be rotated or mirrored and may not line up. So point being, with the physical button, looking at how these little metal tabs or pins that go in the breadboard are sticking out to the side, pin 1 is always connected to pin 2, pin 3 is always connected to pin 4, and when I press the button, then all 4 are connected. Okay, so that's not clear until you look at the data sheet if you're just looking at it in Tinkercad. So, and this data sheet will be scanned with the lecture note PDF, so don't worry about trying to copy that whole thing down somehow. If I switch back over to Tinkercad, I can see that means, okay, so remember the terminals are sticking out to the side, right, sides like this, and Tinkercad kind of labels them differently, right? When you mouse over a point, Tinkercad will tell you what it's called. So terminal 1A is always connected to 1B across the button. 2A is always connected to 2B, and then when I push the button, they're all connected, right? So if I run this simulation, you see that this LED is just always on. I don't have to push the button, right? Because 1A is connected to 1B. So I can trace a path for current through this wire, just across the top of the button. These rows are irrelevant, through the LED and through the resistor to ground, okay? Same if I go up to this one, same thing. I'm actually the way I have the button oriented and rotated 90 degrees here, I just have row 2 of the breadboard hardwired to row 5 of the breadboard. It doesn't matter if I push the button, right? So that LED is always on. This one is always off, not because of using just the same row of the button, but because I have it connected to ground on this side, right? So this LED actually isn't receiving any power, right? This side of the button is connected to ground. This side of the resistor is connected to ground. So actually, if I move that button over one and start, oh, well, sorry, now it's not connecting. But if I add extend this lead to there, same thing. Then this LED is just always on, because that's not how the button works. It is only in option D, where I have my connection to power coming to the top part of the button, and then the LED is connected to the bottom part of the button, which is then in series with the resistor to ground, right? This actually works right. So right now there's an open circuit, there's no connection from here to here. Then when I press the button and hold it down, it closes that and the LED lights up, okay? So this is just one example. This is one part, that was the data sheet for one button. There are other types of buttons out there that might have different pin configurations. I'm pretty sure the one in Tinkercad is similar to the little 4-pin ones you have in your kit. You also might ask, well, okay, if the opposite pairs of pins are electrically redundant, why do you need them at all? It's for mechanical stability, right? Like if you put this in a breadboard or solder it to a circuit board, and you only had these 2 pins on one side, then every time you press down on it, right, it's going to be bending those 2 pins versus having kind of 4 pins in 4 corners, so it's anchored, and then when you press vertically down on it, It's just a symmetric force, and there's no kind of asymmetric torque on it that's going to fatigue those pins. So that's another thing, excuse me, you will see with some other parts later in the semester that, for example, might have multiple ground pins. And you go, okay, well, why do you need 2 or 4 ground pins? Not necessarily for mechanical support, but for thermal support, right? So it's more connections to dissipate more heat, even though in the physics homework diagram you only need 1 ground and having more is redundant. Okay, sorry, give me a second to kind of recover from. Right. So, any questions at all on, again, that might have been kind of fast if you've never seen this before, but questions on the button situation? Okay, we are then going to switch over and do the same thing for a switch. So give me 1 second to switch to the right, no, wrong way, thingy. Okay, similar configuration, except this time, if I can find my mouse, I have toggle switches instead of buttons. So I'm going to activate this. So these switches you will see have 3 pins instead of 4, and the buttons I should have said were called, those were momentary buttons, meaning they have an internal spring action such that when you have to hold it down, right? If you release the button, it pops back to its original position. These are toggle switches, more like a light switch on a wall, right? Like you flip it into one position, it stays there until you move it back the other way. Okay, so again, kind of a black box. It has 3 pins. The Tinkercad view here is not showing you how those pins are internally wired. Which LED will be off with the switch in its current position, and then turn on when I run the simulation and toggle the switch. And yes, this is technically dependent on me remembering to leave the switches in the right position before I do this. So I'm going to pull this off screen for a second and make sure I have that set up right. Give me 1 second. Okay, that's all set up right. Okay, so which switch, if I hit start simulation, which LED will be off and will then turn on when I toggle the switch? lot of good discussion, and I can see people like pointing and working it out, but I want to make sure we have time to get through everything today since last two was next week. So we're at 106 votes. Let's give it 15 seconds. Ten. Oh, you guys got quiet really early this time. This is unusual. 3, 2, 1. Deactivate. Correct answer in this case is C. So about half of you got that right, but then we're kind of evenly split between the other options. So again, we are going to switch over to Document Cam first and look at a data sheet where, again, we have mechanical drawings showing the dimensions of this thing. Different, I don't think, this one, for example, doesn't really have force information on it, but there's a bunch of electrical information down here. So what's the maximum voltage and current rating? What's the contact resistance? And here's the schematic, which maybe isn't as immediately obvious what's going on here, but this is saying that the center pin is always connected to either of the outer two pins. So when you slide the switch to the left, then the center pin is connected to the left pin. When you slide it to the right, the center pin is connected to the right pin. So this one doesn't actually, the way we would draw the circuit diagram for that would be like this, where you have on this end what is called the pole of the switch, and on this end, these are called the throws. So this is a single pole double throw switch, abbreviated SPDT for short. Okay, so there isn't really an off or not connected to anything position for this switch, right? That middle pin, so if I label those pins over here as 1, 2, and 3, then this diagram I have pin 1, pin 2, and pin 3. Pin 2 toggles back and forth between being connected to either pin 1 or pin 3. So that's a little different from your light switch on the wall, which you would call a single pole, single throw switch, right? Where it's either on or off, it's not toggling with them. As long as we're not talking about three-way switches that you can turn off in different locations or something. That is an SPST switch. And you will also see further iterations of these acronyms where there's like double pole, single throw, double pole, double throw, triple, like whatever. So you can have kind of for example, a switch like this, where these two contacts are kind of mechanically linked. So when you flip a single switch, it's actually toggling two at once. I believe that's double pole, double throw, and that's double pole, single throw. So you can go, again, this is the kind of thing you can just go look on Wikipedia and see a table with the diagrams for all the different types and corresponding acronyms. Point being, in this case, we have single pole, double throw. It's wired like this, where the middle one toggles between being connected to the two outer ones. So if we switch back to the laptop and kind of go through these, if I start the simulation, here, remember that you should pretty much never see something with all of its pins in this same row of the breadboard, right? Because that just means you are shorting that thing out. That's just like taking all of the pins and welding them together and making that part do nothing, right? So that one, toggling the switch doesn't do anything. This one is just kind of wired bizarrely, like the LED isn't actually in series with the resistor. This leg of the LED just kind of goes to, when the switch is in this position, the LED is shorted to itself and there's no power. When the switch is in this position, then the LED isn't actually in series with the resistor, right? Power just goes straight through the resistor to ground and sort of bypasses the LED. This one, when the switch is in the down position, right, the LED is just connected to nothing because this row is empty. When the switch is in the up position, this row, again, pin 2 is now connected to pin 3, so power goes through the red wire, through the switch, through the LED, through the resistor to ground. This one, the switch is just wired wrong, right? So that middle pin is not connected to anything, and regardless of which position the switch is in, the outer two pins are never connected. That just toggles which one of them is connected to the middle pin. So due to how the switch is wired, the LED is just never going to get power here, okay? So any questions on the switch wiring? Yes, in the back.
Yeah, so those kinds of switches, there must be a connection on the
Sir, I can only hear the first part of your question. Could you talk a little louder?
Sorry, those kinds of switches, there must be a connection on the middle thing, right?
Yes. So if you want to use this to do something, if you only connect things to the two outer pins, it's never going to do anything because the middle pin isn't connected to anything. Okay? Any other questions on the switches? Okay. Specifically talking about switches because if you have looked at document cam, the document camera, your battery packs have built-in switches. And in my experience, these are probably one of the most common failure points. Okay, so if your circuit, whether it's a lab, a homework, your robot, whatever, if things just aren't working, one of the first things to check is, am I actually getting power? Okay, and you can check if you're actually getting power using your handy multimeter, right? So you should have used this in lab 1, but I'm going to set this to measure DC voltage in the 20 volt range. So remember, this range is the maximum that it will measure for a given range. So 9 volt battery, 6 volt battery pack, 20 volts is good. If you go down to 2 volts, that's going to be too low. You should be able to take your 2 probes, turn your battery pack on, and this might be kind of hard for me to fit. Let's zoom out again. Touch these to the exposed metal ends of the battery pack leads. And if I can do this without bumping everything off screen, sorry. And get 6 volts if everything's working, right? Yeah, 6 point something volts with fresh batteries, okay? Now remember that dead battery does not literally mean 0 volts, okay? So if you start getting a little less than 6, approaching 5 volts, that's kind of actually getting into dead, below 5, that's actually kind of dead territory where it's not going to be able to power your robot's motors anymore. But what if you get 0? Right, you're just getting 0. You swear you are 100% sure you just put fresh batteries in there. You can check that by individually checking the voltage of a battery. Right, I can take an individual battery, check it, and okay, I know I'm getting 1 point, so I know that battery is good. And I know I say I did that on all the other ones. I know they're all good, but I still get 0 on the external. I try to measure the leads of the battery pack. Right, what's going on internally? And again, I think I drew this 1 or 2 lectures ago. All of these are connected in series. They are then connected in series to the switch, which is connected to these 2 wires, right? So everything in series, a break anywhere in that circuit will cause you to read 0 volts. Okay, so thinking about what could physically fail here and cause you to get 0 volts, there's actually a lot. You could have the switch fail, right? So if the switch is kind of going janky, that can be a sign of an inconsistent reading, like you got 6 volts and you swear it worked a minute ago and now it's not, right? If this switch, if something is loose and that switch is something is loose but not completely failed, then just kind of depending on how it's sitting or how you pushed on it last time. The wires themselves could be kinked internally, so this is a good point to talk about different types of wires in your kit. So you have a little box like this. These are solid core jumper wires, meaning it is a single solid cylinder of copper in there, right? And copper is very ductile, so you can see these all have little 90-degree bends on them that make them easy to put in your breadboard. And if you need to, bend something into a certain shape to organize things nicely on the breadboard, you can. If you bend these back and forth over and over and over again, it's going to be like a paperclip, right? Like eventually it's going to break. But individually, these are kind of, usually students aren't bending them around that much. They're unlikely to fail. These are stranded, not solid. So you can see these are much more flexible. And if you were to take your wire strippers and cut these open or kind of zoom in on the ends, you'll see that it's braided like a rope, right? Like it's not a single cylinder of copper. It's a bunch of finer strands of copper. That, excuse me. So if you were going to do something like build a robotic arm, right? Like you wouldn't run and you needed wires to pass through an elbow joint. You wouldn't use the solid core wires because they're going to fatigue fail as you bend it back and forth. These are way more flexible, but if you kink them too hard, right? If I take this and literally bend it over 180 degrees and pinch it, I can fray the wire internally and kind of result in an intermittent connection. You also then have wherever it physically connects to the battery pack, right? If people have kind of been tugging on this over the years, that connection can go loose there. you have these little springs that are pushing the battery contact kind of up against the other side. So I don't know how well this is going to show up on the document cam, but inside, yeah, that doesn't really show up well with the lighting, but if I can get the reflection perfect. So there's a metal plate on this end that connects the two batteries in series, right? There's a spring here for the negative end of one battery, and then this plate connects to the positive end of the next one. That's just a solid hunk of metal, so it's pretty unlikely for that plate itself to fail. But we actually, the TAs and I were just looking at one in lab earlier this week where, so you kind of look at the length of that spring, right? It's maybe, I don't know, close to a centimeter long. There was one where the spring was just so smashed, it was almost permanently in the compressed position, and it wasn't pressing the battery positive contact up against this end enough. So even though all the batteries were good and the switch was working, the break was right there. Okay, so just with this single battery pack, that we just listed like half a dozen things that can go wrong, right? And again, taking that, and now, once you've identified a problem that it's not working, are we going to make you physically repair the battery pack? No, you ask the TAs and they'll give you one that we know is working, right? But we need to verify first that it wasn't just you putting the batteries in backwards, right? Or forgetting to check that the batteries were fresh or something. So again, this might seem like a super, incredibly simple thing. We're not doing any differential equations here, right? But being able to take a battery pack and look at what is actually wrong and use your multimeter voluntarily as a debugging tool, okay? Not just something that we force you to take measurements with on the homework in lab, right? I can use this to measure voltage. I can also use this to test for continuity, which I don't remember if we had you do this in lab 1 or not. 1 second. So this little symbol over here stands for either diode check or continuity check. If you set it to that and touch the two probes together, you guys probably won't be able to hear this, but there's a beep. Okay, I don't really want to hold this up with a microphone because I think it'll be awful, but it's beeping right now. Okay, and the little red light is flashing. So any wire or so, don't use that on things like batteries, but anything that should just be a conductive metal connection, right? Like between this spring and this plate on the battery pack, I should be able to touch that and get a beep, right? Or if I want to test one of my jumper wires or a cable that I think might be frayed or broken, you take those to the two ends, test it, that's how you tell if the cable is bad, okay? So again, this is all stuff that I can't really, I could write those steps down in lecture notes, right? But I think it's a lot easier to actually demonstrate it live. What I want to do, because I promised that actually took a lot more time than I thought it would, but I promised you guys we would get to use Tinkercad today. So get out your laptops, and what I want you to start doing is, now that you know how buttons and switches work, this is the circuit we're going to ask you to build for pre-lab 2, right? And we kind of did some Tinkercad stuff, oops, earlier, and I got some questions about like, how did you make, somebody came up to me after lecture and asked, how did you make your circuit so neat, right? Like mine is really messy, how did you do that? And this is kind of another skill that is not really a textbook thing, but is one of the more important things to come out of this class is, how do you start with a circuit diagram and translate it to physical layout on a breadboard, right? So this circuit has 4 LEDs, 4 resistors, a button, and a switch, right? And a battery pack. It's wired such that when these 2 LEDs will be off by default. When you push the button, they both turn on. This switch will toggle which one of these LEDs is on, right? So one of these will always be on, and then when you toggle it, it'll turn off, and the other one will turn on. So there are effectively infinite possible ways to physically arrange that on a breadboard. What matters, I think, is to pick something that makes sense to you, right? So, you know, I've kind of harped on repeatedly not getting geometric layout in the circuit diagram mixed up with electrical series in parallel or physical layout in the real world. But that doesn't mean you can't do that if it's convenient, right? So like the way I have all of these drawn with 4 sets of LEDs and resistors in parallel, if it helps you to arrange them like that visually on the breadboard too, fine. Just make sure the electrical connections are right. Okay, so you could tackle this and say, I'm going to lay out all the LEDs and resistors first, and then I'm going to figure out how I'm going to wire them to the button and switch. You could put the button and switch there first and say, then I'm going to attach the LEDs and resistors after that. kind of like pick a point and build around it. There isn't a right or wrong way to do it. It's a matter of personal preference. But what you don't just want to wind up with a tangled mess of wires at the end where you can't tell what is going on. Okay? Color coding, also very important. Remember, the convention is usually to use red for positive and black for negative because that matches the wires coming out of your battery pack. But you might say, I want to use green for the connections to the button or something, right? Orange for the connections to the switch. Purple for between the resistors and the LEDs if you use jumper wires like that. You can also, any of these components you can wire directly together in the same breadboard row, right? You don't always have to use jumper wires. But if using extra technically unnecessary jumper wires helps you arrange things more neatly, that's fine. Okay, so again, no right or wrong way to do it. But with kind of the 9-ish minutes we have remaining, I want you to get started on this so we have time if people do have questions kind of going into lab 2. And again, when going into lab 2, you're going to do this in Tinkercad, but you're going to show up and the TAs are going to hand you this hand a pre-built version of this to you on a breadboard that is broken. And the difference between Tinkercad and the real lab, right, is Tinkercad does not model things like a fatigued battery pack switch. Okay, things can be in the wrong place in Tinkercad. You can get things wrong in the breadboard or have things rotated the wrong way, but it's not going to have dead batteries, it's not going to have a broken switch, it's not going to have frayed jumper wires. So this is just kind of a prelude to other things that can go wrong in lab. You can also, I should have mentioned, test this as you build it, right? Rather than trying to build the entire thing and then hit start simulation and nothing works and you don't know why. This is another kind of similar to debugging. Think about programming, right? Like you might get individual functions working one at a time before you try and just run the entire program. So, you know, you could say, okay, I'm going to chop this circuit in half there, right? I'm going to do just the 2 with the button first, get that working, then I'm going to do the 2 with the switch, or vice versa. And again, even if this kind of seems maybe mundane because it's just buttons and LEDs, this becomes really important with the robot at the end of the semester because your breadboard gets crowded. Right? If these robots aren't that big, you've got the little half-size breadboards that are just a few inches long. So planning where things go and then being able to trace them when something isn't working. So your robot's going to have 2 motors, at least 2 motors, circuitry to control those motors, and at least 2 or 3 different sensors. So you're going to have easily half a dozen different things that are all connected to the breadboard and then connected to the Arduino. Right, so if you just lose track of what wires are where, it becomes very, very hard to figure out why something isn't working. I didn't mention, remember to use the power buses. Don't just take your wires from your battery pack and go directly to some breadboard row. You wire the battery pack to the buses, and then you have easy access to power and ground kind of running up and down the whole length of the breadboard. The power buses on opposite sides are not connected. So, for example, you could say, I'm going to use the left side of the breadboard. You know, if you think about the breadboard kind of like this, right? You could say, I'm going to do these on the left side and these on the right side. You need to use a jumper to connect power over to the right side power buses. You could also rotate this whole thing 90 degrees and say, I'm going to do all the LEDs, kind of like I had some of the examples going across the breadboard, right? No right or wrong way to do it. And if you have questions kind of as you're working on this, you know, I can walk around. Feel free to raise your hand. Yes?
Was that symbol the sideways, short-sided H? Is that a button or a switch?
Shorts, this thing?
Yeah.
Yes, so sorry, the question was, what is this thing? That is the symbol for the switch without drawing the electrically redundant pins. So,
Gotcha, okay.
you know, if we looked at the circuit diagram on the data sheet, it was drawn, sorry, symbol for the button. The diagram for the button on the data sheet was drawn like this, but again, these are sort of electrically redundant because they're disconnected, so that is electrically the equivalent of drawing it like this or like this, where,
So on the left and the right, it's the same object?
no, sorry, so electrically these are equivalent. In terms of the physical part it represents, this represents a switch and this represents a button. So in Tinkercad, this, and I think this is a little more clear in the pre-lab too, that's a button and that's a switch. And there's kind of some resemblance between, again, the circuit diagram and what the physical part is. You can see how you, like, pushing on that would make this close that contact, so it represents the button.
Thank you.
Yep. Yes.
So to place these in series, or in, like you have them in parallel, there's two first resistor and diode,
Mhm.
and then you have the switch. Those are both in parallel as well with each other.
If you think so, if you think about kind of branches of the circuit as opposed to individual components, right? So I kind of think of this whole part
Right.
as a branch and this whole part as a branch. Those two branches are in parallel, but like technically the switch is not in parallel with that resistor, right? Like the individual, or like this LED is not in parallel with that LED, but these two branches are in parallel with each other. Does that make sense?
Yeah.
Gotcha. Sure, if I can. So remember how you have your LED wire. Remember how, well, not flipped, so they both like the same room. They both like the same room. You never really have The breadboards have a gap in the middle. A lot of parts are sized such that they will fit across that gap. So I see a lot of people kind of putting the buttons on one side or the other. It can be more convenient, and this will definitely happen with some of the integrated circuits we'll see later in the semester, to make use of that gap in the middle. Okay, when doing that, I think that just kind of you don't have to do the buttons like that. Like I just worked through it with someone who had it working in a different position. My default with the buttons is to just have them cross the gap. I just realized it is 12:05. You know, I don't want to run over time, but I also stick around after lecture anyway, and there's not another class in here until 1. So if you would like to go, you're free to go. If you want to stay and just like work on pre-lab 2, I can hang out and answer questions either way.